Okay, so today we will be talking about phase diagrams, and this is going to be the beginning of chapter 11. If you remember in the previous chapter, in chapter 9, what we talk about how can we change the mechanical properties of materials. We talked about different mechanisms that can enhance the strength of the material. And we talk about the solid solution alloying, the cold working, and then also we talked about the grain size reduction. We said that the more barrier that we can place in the front of the dislocation, as we can prevent the dislocation motion, we can make the material more stronger. Because the result of dislocation motion, you get plastic deformation. Plastic deformation, that means if it's easy for the dislocation to move, that means it's easy to plastically deform the material. So we learned about 3 different mechanisms that can make the material stronger. And then also we learned about how can you enhance the ductility of the material, because as you make the material stronger, at the same time you're going to lose the ductility of the material. Okay, and before I start today's lecture, I would like to remind you with this slide. So if you remember, we say that by doing solid solution alloying, we can increase the strength of the material. For example, if we have a copper has a certain tensile strength around let's say 210, and then once you start to make a solid solution alloying, once you start to add nickel to copper, okay, so as you add 20% nickel to copper, so we have 20% nickel, 80% copper, the tensile strength gonna increase, and gonna peaks out at around 410 megapascal. Okay, so as you can see that we can enhance the mechanical properties by doing the alloying, right? Similarly, if you're increasing the strength, you're going to lose something about the you're going to lose the ductility. So you see the ductility is bottoming out at a certain value where it peaks over here. Right? Right. Then solid solution is a very important topic, because if you do solid solution alloying, you can change the properties of the material. But the question that we have, okay, now at 60% nickel and 40% nickel, 40% copper, 60% nickel and 40% copper. The question is, at different temperature, are we gonna have a liquid phase or solid phase, or maybe a mix of solid and liquid? Because what we know that copper has different melting temperature than nickel. So what's gonna happen if you start to heat up the alloy that you have? And now copper has a melting point that is much lower than lower than the nickel. So if you have a mix of these two components, what is the resultant melting temperature? We can imagine that at those composition, the solid will partially melt, and then it's gonna completely melt, right? So this chapter 11, will tell you something about, we call it phase diagrams. Phase diagrams are going to show you a graphical representation of a relation between temperature and composition. So the y-axis you have the temperature, and the x-axis you have the composition. And then it's going to tell you at a certain temperature, a certain composition, a certain temperature, what are the phases that exist at that point. And also, what is the composition of that phases? How much of this phase that you have? Why we are talking about this? Because if you look at the figure over here, as you can notice that this alloy, it's made of 2 components, اللي هو nickel atoms and copper atoms. But what you can notice clearly over here that these 2 regions are different. The way the atoms are organized, the way the nickel atoms and copper are arranged is different in this point compared with this point, right? So this region, we can call it phase, and a phase is a uniform portion of a material where you have physical and chemical, similar uniform physical and chemical characteristic. Okay, so this is a phase and this is a phase. So the question that we have right now, how many phases exist? One phase, only one phase, so we don't see this phase over here, phase B, or we have two phases, right? And the other question is, in phase A, how much copper I have and how much nickel I have. Similarly, in phase B, how much nickel I have, how much copper I have. And then the other question is, how much phase A I have compared to B, right? Whether I'm having 80% phase A, 20% B, or have 20% A, 80% phase B. Right? All these are important questions, right? And the phase diagrams can provide you all this information, and we need to learn how can we extract this information from the phase diagram. طيب فإذا phase diagram is the graphical representation of the phases that might exist as we are varying the temperature with the composition. Okay, let's take a simple example that maybe you're familiar with. Okay, let's look at this over here. Okay, in this example, it's a phase diagram. It's a phase diagram where we are varying the temperature and the composition, right? So I guess maybe you have tried this before. So you're trying to add sugar to the water, and you know that the sugar can dissolve in a water, right? As you're adding sugar, still you're going to end up having a syrup, which is a single phase. So at this point, at room temperature, if you start to add sugar, you still have a liquid phase, until you hit this line over here. Once you pass this line, you start to have two phases, liquid and solid. And the reason behind that, because there is a solubility limit for the water, right? So if we add more sugar, then the water cannot accommodate those sugars. What's going to happen is you're going to have two phases. So by using this phase diagram, we can know at a certain composition and temperature what are the phases that can exist, right? So for example, at 80% sugar at room temperature, you have two phases. So at this point, you have two phases. You have liquid and you have solid. Okay, also we can play with it. Okay, what we can do, for example, we can, if we are at point A at room temperature, 20 Celsius and 70% sugar, now you have two phases, right? So if you heat it up until point B, you can, by increasing the temperature, you can enhance the diffusion, you end up having a single phase. So at this point, you have a single phase, which is a liquid phase, right? So, and then if you add more sugar at this point, then you're gonna cross the solubility limit where you're gonna have two phases. So the main message of this slide is this phase diagram can correlate the temperature with the composition. So at a certain temperature and composition, what are the phases that exist? One, okay? And then also there is a solubility limit. I mean, if you pass a certain lines, you're going to end up having two phases that can exist together. Right? Wonderful. Now, that was an example when you have a different phase. You have a solid and liquid, and you want to mix them. Okay. So in this example, we have this is an image for a solid solution. This is an image for a solid solution, so it's completely solid, right? So completely solid, and this alloy has two components, which is aluminum and copper. Okay, so aluminum and copper, they're gonna dissolve in each other to form two types of solid phases, right? And those solid phases, we call it beta and alpha. One of them is rich of aluminum, and one of them is rich of copper. And one of them is rich of copper, but still can accommodate aluminum. And one of them is rich of aluminum, but still can accommodate copper. So you have two different phases, as you can see here. One is lighter, one is darker, right? The two solid phases, right? So we need to know, what are the phase diagrams for different systems. This is very important because it's going to tell us what will be the phases that are going to exist in the material. Some phases will enhance they're going to impact the mechanical properties of the material. Okay, wonderful. Now, if you remember that we said before that nickel and copper, they can completely dissolve in each other, right? Regardless of how much you add in copper, nickel to copper, at the end of the day, they're going to dissolve in each other because if you remember, we say that they have similar crystal structure, electronegativity, and also similar radius. So they can miscible in each other and they completely dissolve in each other to form a single solid phase. ايش معنى الكلام هذا؟ What does it mean? That means here, because aluminum and copper, they are not completely solid in each other in a solid phase. That's why you see two solid phases, right? Two solid phases. However, when we talk about nickel and copper, because they completely dissolve in each other, in solid phase, you're going to have a single phase, and in a liquid phase, you're going to have a single liquid phase, okay? Okay, wonderful. So this is why we're going to start this chapter 11, by talking about this one of the simplest systems phase diagram, and then we're going to get to more complicated ones, inshallah. Okay, this is how the phase diagrams for the copper and nickel look like. Okay, so let's walk you through this diagram. So in the y-axis you have the temperature, in the x-axis you have the composition, right? The composition of the alloy. So if it's 20% nickel, معناته 80% copper معاه. So an alloy that had 20% nickel, 80% copper، تمام؟ 60% nickel معناته عندك 40% copper. ممتاز. Okay, and this is the y-axis. We have the temperature in Celsius. So for example, at 1000 Celsius, 20% nickel, we have a solid phase. Have a solid phase because we say that the copper and nickel, they can dissolve in each other to form a single solid phase. So they form a single solid phase. We call it alpha. It has crystal structure FCC. Okay, wonderful. Okay, and then if you go to 1500 Celsius, so at 20% nickel, 1500 Celsius, how many phases you have? You have liquid, right? So if you have a liquid phase, so they completely dissolve in each other to form a single liquid phase, right? This is what's special about copper and nickel, because they can completely dissolve in each other. So at the end of the day, we have a more simple phase diagram. One solid phase, one liquid phase. ممتاز. Another important point over here is at 0% nickel, you have pure copper, right? So at 0% nickel, you have pure copper. Okay, notice that for pure copper, the melting temperature is around 1100, okay? So it's around 1100 Celsius. معناته إنه you have solid phase, solid phase, solid phase. Once you heat it above 1100, the solid phase is going to be going to transform to liquid phase. طيب. Now let's go to the other side. So let's go to the when you have 100% nickel, that means you have 0% copper. Ya salam. So what's going to happen? So you know that nickel, if you heat it up, it will not transform to liquid before around 1400. تمام? So that means nickel has higher melting temperature compared with the copper, right? So when you start to make a solid solution of these two components that they have different melting temperature, you expect that a portion of the solid will melt, right, as you are heating up before it's completely transformed to liquid, right? This is why in the middle here, you see that you have a region where you have a transition state, a transition region. We have, in that region, you have two phases, liquid plus alpha, right? Solid alpha. Okay? So, for example, if you are at 60% nickel, right? Here at 1000 Celsius, at 1100 Celsius, here you have a solid phase, right? If you keep heating up, you hit the solidus line, and then you get into a region where you have two phases, right? You have liquid plus alpha. If you continue heating up, you're gonna completely melt your material to have a liquid phase. طيب. Okay, so the question that we need to answer now, how many phases exist at a certain point? So this is an isomorphous binary phase diagram. Binary because you have two components. You have a copper and nickel. It's what's called binary. One. Two, isomorphous because they can completely dissolve in each other. So this is why we call this one isomorphous binary phase diagram. So in the isomorphous binary phase diagram, the question is, at a certain point, how many phases exist? Okay. Again, so at 60 weight percent nickel, and at 1100 degrees Celsius. So at this point, how many phases exist? One phase. You have a solid alpha. That means all the nickel will come together to form the solid alpha phase, right? And then at this point you have two phases. At this point you have one phase. Right. The second important information is now at point B here we said that we have two phases اللي هم liquid plus alpha, right? So at this point you have two phases, liquid plus alpha. The question is, in the liquid phase اللي هنا موجودة, liquid phase, how much nickel you have, how much copper you have, right? And similarly for the solid phase, how much copper you have, how much nickel you have. Because at this point, part of the nickel gonna form the liquid, and part of it they're gonna form the solid phase, right? In order to determine the composition of the liquid phase, you're gonna draw, and the solid phase, you're gonna draw what's called a tie line. So tie line, you're gonna draw it to head the liquidus line over here and the solidus line. So what is the liquidus line? Liquidus line above which you have liquid, completely liquid, and solidus line below which you have only solid phase. So you're gonna draw a tie line connecting these two regions. And then once if you want to know the composition of the liquid phase, you're gonna go from your point B to this point, to the intercept over here, and then you're gonna drop down to see what is the composition of the liquid. So the composition of the liquid, you have 32% of the liquid is nickel, and then for the solid phase, 43% of the solid is nickel. Tamam? At point A, the composition, how many phases exist? One phase exists, liquid phase. What is the composition? 35% nickel, and the remaining is copper, right? So once you have more than one phase, you have to worry about you have to use the tie line in order to determine their composition, right? The other important information that we can extract from this phase diagram is, okay, if at this point I have two phases, how much I have liquid, how much I have alpha, solid alpha, right? In order to determine that, we're going to use what's called lever rule. Right? So you're gonna use this tie line that you draw, the tie line, and then you say this is your point. If I want to know how much liquid I have, I'm going to take the distance between the opposite side, اللي هو هذا S, from the solid to your point, S, and then divide it by the total distance, اللي هو R plus S. This is why the weight fraction for the liquid يكون عبارة عن S over R plus S. And if you want to know what's the weight fraction for alpha, I'm going to do it similarly. I'm going to say, I want to know how much alpha I have in B. I'm going to say the distance between the B and the other phase اللي هي R over R plus S. طبعا ال S هي عبارة عن ايش؟ عبارة عن C alpha تمام minus C naught. ال R عبارة عن C naught minus CL. تمام؟ Okay, so by doing so, we can know how much liquid I have, how much alpha. طبعا هذه عبارة عن fraction. So if you add them, you end up having 1, right? So the total should be 1. So the fraction of liquid plus fraction of alpha should at the end equals to, when you add them together, they should equal to 1. Okay, so what we learned today is we learned that by using the lever rule, we can know how much we have from each phases. And also by using the tie line, we can know the composition of each phase. And by looking at the phase diagram, we can know how many phases exist at a certain temperature and a certain composition. This is why phase diagrams are very useful for material scientists and for materials engineers. Why? Because you can know what are the phases that exist, and then those phases sometimes they have different mechanical properties. Okay. Before we end this lecture, I would like to go over this slide very quick. So if you are at point A, you have a single phase, اللي هو liquid phase. Okay, so liquid phase, the composition is around 35% nickel. If you start to cool down, once you hit the liquidus line, you see that, and so at point B, you start to nucleate the solid phase, right? You see the blue dots over here representing the solid phase. Once you continue cooling down to point C, the solid phase start to grow larger and to consume the liquid phase. Once you hit D, now you have more solid phase. Once you get to E, all the liquid that you have transformed to solid phase. So as you can see that there is a changing happening in the microstructure of the material as you're cooling down from a certain temperature to another at a specific position. Okay, I think this was a good introduction to chapter 11. And next class, we're going to talk about what's called binary eutectic system. So in this class, we talk about isomorphous binary system, where you have two components that can completely dissolve in each other. In next class, we're going to talk about what's going to happen if you have two components they do not completely dissolve in each other. So as you can see here, you have two solid phases, alpha plus beta, right? And you get more complicated phase diagram compared with the previous one. And this, inshallah, we're going to talk about it in next lecture, inshallah.